I said, I like to schedule and I like to make these review sessions very open-ended and kind of focused on what it is you need from me rather than just kind of going off of a preset script. So we do have the practice exam in front of us if we want to go that direction. If there are specific things that you want to talk about kind of off the start, I'm going to turn it over to you first. So is there anything specifically that you want to discuss or go over before we kind of do anything more generic?
Yes, I have some review questions on chapter 1, chapter 2, chapter 3.
Okay.
Go over. I won't take time for anyone else. If we have some, like, I have one for versions where it's a question that has, there's this much nitrogen going inside this fertilizer, and 50% is going to the river. I have a exact question.
Guessing it's nitrogen runoff.
Yeah, it should at the very bottom. I have opened it. I've done it over multiple times. I think on my third.
Okay, so we can probably start with this statement here. There's not going to be a conversion question this complex on the exam. And the main reason for that is that would be the entire exam. Now that being said, you know, in terms of what question you're being asked, if the river flows at an average rate of that many cubic feet per second, what is the additional concentration of nitrogen in the river due to the farmer's fertilizer? Yes, there's a whole lot of information that goes in there. And so, I mean, what we can start with is we can use the data here to go about figuring out kind of the top half of that conversion and then the flow rate for the bottom half. So first thing that we could do is we could say, okay, if we have 1,250 kilograms of fertilizer and 10% of it is nitrogen, well, that would mean that 125 kilograms of nitrogen are being used every year. And then a further 15% of those are being washed into the river as the river flows. So 15% of that 125 now gets us to 18.75 kilograms of nitrogen in the river. And ultimately, the problem wants us to express that in milligrams of nitrogen. So we would need to convert the kilograms to milligrams. Well, we could do that. There is a kilogram for every 1,000 grams and a gram for every 1,000 milligrams. In total, I'm gonna switch to scientific notation here, just for the sake of cleanness. 1.875 times 10⁷ milligrams of nitrogen. So that's our runoff in terms of nitrogen. The other part of it, so again, this is 1 year's time. The other component of this is we have to do the conversion from cubic feet to liters. And then we have to calibrate that to 1 year's time as well.
So could we also do this, turn this to 1 second, or do we have to turn cubic possibly?
Well, you have to get them in the same time. So yes, you could take that 1 year and pare it down to a second. Actually not, it would not take that much to do. So if this is the per year rate, you know that every year has 365 days. Every day has 24 hours. Every day has 24 hours. Every hour has 3,600 seconds in it. So if we calculate that part out, divide by 365, divide by 24, divide by 3,600, that pares it down to a much more manageable number, 0.5946 milligrams of nitrogen every second. Now all we need to do is convert this cubic feet into liters. You'll need a volumetric conversion for that. So the conversion we can use out of the book off page 20 says that 35.31 cubic feet are equal to 1,000 liters. So if I do that conversion, .5152 times 1,000 divided by 35.31, you get 14.59 liters. So every second, 0.5946 milligrams of nitrogen flying its way into the river. That river also is churning 14.59 liters in that same second. The additional concentration of nitrogen then would just be the division of those two. 0.5946 milligrams divided by 14.59 liters. .075 times 10 to the negative second milligrams per liter. And it's pretty close. Yeah, 0.408 they say. We rounded to 3 sig figs as well, which I'm not sure exactly why they did. Unless I'm missing a detail somewhere. I guess percents. You get the same answer within rounding. So where you were going to run into problems with this one is if you tried to do it all in one big calculation step, you're going to get confused. It's much easier to kind of just break it into the pieces and then divide the pieces by each other when you did. But like I said, this is more complicated than the scope of what you're going to see on the exam. The reason problems like this get thrown in there is basically as challenge. You can do that. You certainly can handle whatever I'm going to throw at you on Friday. But anticipate again. This is a 45-minute exam basically. Anticipate that those 6 practice problems are probably going to take you 5 to 10 minutes each. Probably shading more on the 5 side than the 10 side. There is going to be one question in there. I think you probably could figure out you're going to have to do an empirical formula. That empirical formula problem is probably going to be closer to the 10-minute side, just because you got to do all the calculations, all the conversions to moles, the comparison, the analysis, and then the molecular formula. That's about as long as it's going to go. Everything else, expect on the shorter side of things. Yeah.
The sample problem with like the electron configuration stuff.
Okay, so electron configuration is probably gonna come along as something similar to one of these. Give the noble gas configurations or give the complete configuration. So very similar to what you saw on the quiz. Write the configuration for this atom or for this ion. So in this particular case, and this was my exam a couple of years ago. And in that exam, I asked for a noble gas configuration as opposed to the complete. Now for indium here, we would be looking at going backwards, we'd be looking at krypton, 5s2, 4d10, 5p1. Now, the reason I chose this particular example was this isn't an exception in terms of the normal configuration, but it is an exception in terms of the ion, because indium, like any other atom, is going to go by that rule where we remove electrons from the outermost energy level first. So when we go from indium to indium-3, notice we're going to lose these 3 outermost electrons, the ones in the 5th energy level. That means that all that's left over is the 4d10. So you are right to anticipate that electron configurations will make an appearance somewhere in the exam, either in the multiple choice section or as one of those short answer questions. If it's a short answer question, it'll be along these kinds of lines. 2, 3, maybe 4 examples, combination of atoms and ions. So the thing that you have to remember, and this is where some of you generally fell a little bit short, what you have to remember is that if you are making an ion, positive means we take away electrons. Negative means we add. I think that was probably the biggest mistake in the configurations. Most of you understood how to do them. But when I asked you to do selenide, Se-2, I got a number of people that gave me argon, 4s2, 3d10, 4p2 instead of 4p6. Those two electrons are added, not subtracted. Remember, the charge indicates the imbalance of the electrons. Are there extra electrons or are there fewer electrons? Sorry.
Like 1 to the 19 is 1.
Sure. Okay, let's do number 19. So we are told that we have anti-rearing, which is the pigment that's found in acai berries. What we want to do is calculate the number of carbon atoms in 1.5 grams of this particular chloride. Now, we've already been given the molar mass of the chloride, so we don't have to spend time calculating out the sum of 27 carbons, 11 hydrogens, 6 oxygens, and a chlorine. And ordinarily, for a problem like this, you will be given the molar mass to save you some time. Because ultimately, I'm not testing your ability to calculate a molar mass. I'm kind of assuming you know how to do it. Maybe there'll be a molar mass question in the multiple choice. Certainly not here. Usually if I'm going after a mole concept kind of question, it's exactly that. It's, do you know how to use the information? So what we need to think about, we're gonna abbreviate here. We're starting with grams of AC, the anti-rearing chloride. What we need to go to are atoms of carbon. Now, if you remember the mole map process that we did in chapter 2, you'll know that there's a pathway that we can go to do just that. We're going to turn this into moles. We can use the chemical formula to turn the moles of the compound into moles of carbon. And then once we know the moles of carbon, we can turn it into atoms. So we have all that at our disposal. We just got to know how to do it, know what to use. Now, the first step, pretty easy. We're going from grams of something to moles of something. We know molar mass is going to be involved in that. So 1.5 grams of AC, we're gonna turn it into moles. 1 mole of AC is 630.97 grams. So that gets rid of our grams of AC. Now we have moles of AC, we want to turn it into moles of carbon. Anytime we are going from compound to element, we're going to use the balanced, we're going to use the chemical formula, getting ahead of myself. Balanced chemical equations, that's Monday's lecture. We're going to use the chemical formula to relate the two. We know based upon the chemical formula, every molecule of AC has 27 carbon atoms in it. Or if we want to stay in the mole business here, we can say that there are 27 moles of carbon. Again, the molecule to atom ratio is the same as the mole to mole ratio for a compound. So I can say 1 molecule of AC has 27 carbon atoms in it. I can say 1 mole of AC has 27 moles of carbon in it. Because the mole means the same thing for both scenarios, it's the same number, the ratio is going to be exactly the same as well. Doesn't matter if I'm talking about 1 atom or 1 molecule or a whole cluster of them. At any rate, moles cancel out. The last step, we want to go from moles to atoms. Anytime we see a conversion between the macroscopic moles and the microscopic atoms, molecules, formula units, we know Avogadro's number is going to be involved. That's the only place where we're going to use Avogadro's number. If we're staying macroscopic, if we're going grams to moles, moles to grams, we're using molar masses. If we're going moles to moles, we're using chemical formulas. But if we go between moles and atoms, moles and molecules, that's where we're going into those big time numbers. We need Avogadro's number for that. 1 mole of carbon is Avogadro's number. 23rd. Atoms. When moles cancel, one and a half times 27 times Avogadro's number, divided by 630.97 to 2 significant figures, I get 3.9 times 10 to the 22nd atoms of carbon. When we are asked to calculate a number of atoms, that number should be big. It should have a relatively large scientific notation exponent. If our number is missing that, then we need to go back and look at our calculation again. Probably one of the other common mistakes, not necessarily with one of the quizzes that we've taken, but just in general, is getting a problem like this, being asked to find the number of molecules of something and giving me an answer like 2.75. Doesn't make any sense. How can I have 2 3/4 molecules of anything? I go and do the calculation, realize it's actually 2.75 times 10 to the 19th. They just forgot to put on the times 10 to the 19th part. The little things. Always the little things. So make sure that you're aware of that. Make sure that before you move on to that next problem, your answer makes at least a little bit of sense. We're talking about atoms, it should be a big number. We're talking about molecules, it should be a big number. We're talking about moles or grams, the number should be relatively smaller. Doesn't mean that you won't get an occasional answer that's a couple of thousand. Although for moles, that'd be kind of unusual. But you might get a gram number that's a couple of thousand, or maybe even a million. But it's never going to be 10 to the 30th. Because how do you even begin to measure that much mass? All right, we want to look at number 20 as well. Okay. Number 20 just requires you to use an equation off of your equation sheet. So remember that Hertz is the same thing as reciprocal seconds. So if you put that number in times Planck's constant is in joules times seconds. You multiply that by reciprocal seconds, they cancel out. The unit you're left with is joules there. All right. Other questions still?
The question on the chapter here too. About the second ionization energy. Is that something we're going to need to know? Or I don't know what you guys are talking about.
We haven't talked about that yet, at least not in this setting. As far as that goes, if you are asked questions about trends, they will be about the first ionization energy. That's the trend I talked about in class. Now, that being said, if you had a homework problem or otherwise, I was talking about an ionization energy different than that, all you need to do is shift however many boxes over for the number of ionizations that have already occurred. So if we're talking about the second ionization energy, we've already done one energy. We've already removed one electron. Basically, all that means everything has shifted over and positioned one spot. If you do that shift, the periodic trend still holds in terms of position on the table and the exceptions between groups 2 and 13, between groups 15 and 16. Everything still holds. You just have to move all of those over. So what that means is that instead of the noble gas having the highest energy, it's actually giving the alkali metal. Because after that first energy, the alkali metal now has an electron configuration of a noble gas. The noble gas configuration is the most stable, and therefore it's going to be hardest to remove. So everything else kind of falls into place from there. So again, you're not going to see that on Friday, but if it were to come up in another place, that's how you handle that problem. Basically, you visually shift everything over one spot to the left, and then you reapply the trend with everything in its new position. The order comes out exactly the same as you would have predicted otherwise.
So the review questions on the chapter reviews, are those can be ordered on stuff?
Well, so in the chapter reviews, I'm only allowed to pick objectives. I'm not allowed to pick specific problems because they're adaptive assignments. And the reason I chose adaptive assignments is because it uses the entire book as opposed to a pre-selected set. And so because of that, anything that is related to that concept can be pulled, which is why your fertilizer question got pulled. Why the second ionization energy question got pulled, because the objective I chose would have been recognize periodic trends in ionization energy. Well, obviously, that's a trend in ionization energy. You just don't happen to focus on anything other than the first ionization energy. In the case of that fertilizer problem, being able to do unit conversion calculations, that's a unit conversion calculation. It's just a really complicated one. So because I'm picking objectives, concepts, themes, rather than individual problems, sometimes there are ones that sneak in there that are harder than what I would anticipate or expect you to know how to do in a testing situation. So just take that under consideration. If you get something that's just, wow, that's harder than anything we talked about in class, chances are it's harder than anything we talked about in class. You know how to do it, great. You're not going to be asked to do anything that complicated on Friday. Now, do you have something?
Yeah. We're on 5.
Five?
No, I'm not 5.
Yeah. All right, number 5. So is it the multiple choice question, or are you reading off of the other one?
Yeah, no.
Okay. All right, so number 5 is, it's an easy question when you sit and think about it. If I had equal masses of each of these substances, which would occupy the greatest volume? Well, what this really is, this is a density question. Remember that density is mass over volume. Well, if I'm holding the mass constant, the thing that is affecting the density, and whether it's a high density or a low density, is only the volume. So, density and volume have an inverse relationship. The higher the density is, the less volume it's going to take up per unit mass. So with that in mind, which one of these is the correct answer? Yeah, it's D. We're looking at the opposite trend of this. We're looking for the highest volume, which means we should be looking for the lowest density. Lowest density comes in the form of cocoa butter, D. So that question is really just kind of me going after, do you understand how the variables in density are related to each other? It's a simple mathematical relationship kind of question. But you'd be surprised how many people get questions like that wrong because they get the concept confused in their heads.
Say, someone didn't know that same volume parameters. How would someone know? Is there a result?
Well, so you could set a value for mass, just arbitrarily pick one. Let's say that you have 3 grams of each of the substances. You could solve for volume in each of those, since since volume is equal to mass over density. So you could take 3 divided by 0.917, 3 divided by 0.997, and calculate all of those, and you'd arrive at the same answer quantitatively. You just have to, because it is an equal mass, the mass that you said, I just picked 3 out of random. You could have chosen anything. 22? Okay, so these are conversion questions. Now, B is going to be easier for us to do, at least in terms of the fact that those are both English to metric conversions, and we're going to have the English to metric conversion table at our disposal. For A, because the metric table is not being given to us, we are going to need to know how to do that conversion. Now, these are really common metric prefixes, so it shouldn't be that hard to do. It's just a matter of putting the right steps in the right order. So we know we need to go from milliliters to liters, and from liters to kiloliters. Now, if you knew the conversion directly, you could do it. It's 1 to a million. But assuming that you don't know that off the top of your head, this would be the way to go about it, because you should know, based on your experiences with the metric system, that there are 1,000 milliliters in a liter. Milli means 1/1000th of a liter. And you should know also from your experience that there are 1,000 base units in a kilo. So if you take 1,000 times 1,000, that's where the million comes from. 1733.35 divided by 1,000, divided by 1,000 again. You can get your answer as either 0.00173335 kiloliters, or in scientific notation, 1.73335 times 10 to the negative third kiloliters. I would accept either answer. In fact, my calculator automatically put that into scientific notation for me. That's just kind of its default for anything that is less than 0.01. Now, as far as significant figures are concerned, all of those digits are significant, so you need to include all 6 of them in your answer, because the conversions there are exact. They're defined values. Now, the tough part in B is we've got a unit of a combination of units. Now, there's 2 ways to go about this kind of conversion. We can do the all-in-one string, where we start with 8.73 grams over 1 milliliter. And then we go through the process of converting the grams into pounds in the process of turning the milliliters into quarts. We could do that all in one string. But where my caution would come in, again, this is one of the common places where people make mistakes, is if you have had trouble with units in the denominator of fractions in terms of getting the fraction to convert correctly, my suggestion to you then would be to separate the 2 conversions and then divide them by each other at the end. Very similar to what we did in the fertilizer problem that we started with. We split the conversions, calculated each one in turn, then divided at the end. We could do the same thing here. And so long as we don't overround, we'll come up with the same answer. Now, if we do a whole bunch of rounding along the way, yeah, there's going to be rounding errors introduced. That's not going to be a good thing. So either way that we do it will be okay. So I have 8.73 grams. My conversion table here says that there are 454 grams in every pound. So 8.73 divided by 454 would give me 0.0192 pounds. And then 1 milliliter, we want to convert that to quarts. We know that 1,000 milliliters is equal to 1.057 quarts. So 1.057 divided by 1,000. 1.057 times 10 to the negative third quarts. We could divide those two numbers by each other now. And to three significant figures, we would get 18.2 pounds per quart.
Last question.
Yes.
Why did you put 1 instead of the 8.73?
I'm sorry?
Why did you put 1 instead of the 8.73 for the milliliter?
Because the 8.73 describes the grams. It's 8.73 grams per milliliter. So there's only 1 milliliter. If it wasn't, then we'd be able to reduce it further. You know, if it's 8.73 divided by 3 milliliters, we would reduce that and turn it to whatever 8.73 divided by 3 is. So when we have a combination unit like this, the denominator is always 1. Now, if we had done this in one long string, all that we would have done is basically this conversion here and the flip of this second conversion. We do it that way, 8.73 divided by 454, multiplied by 1,000, divided by 1.057. We get the same 18.2 when we round to the significant figures. So like I said, both methods are equally useful.
For the test, or you might have already said this again, sorry. Do we even know like 1,000 milliliters or 1 equals that we really have a conversion case?
No, so if you go here, so here in Top Hat with all the other exam materials, you will find this is the exact equation sheet that you'll be given. And in that equation sheet, you'll also be given this table of values. And so on this particular table of values, you have a relationship between grams and pounds. You can just pull it directly from the table into your conversion factor. The reason I'm using this table instead of the one in your book, that one's got more conversions on it. Because I actually think that the one in your book's a little bit scant. So there's not very many conversions on it. It doesn't cover as many situations as that one does. That was from an older version of the text. So this periodic table that you'll get. And this is the equation sheet that you'll get. So as you're kind of preparing, as you're doing practice problems, not a bad idea to have that kind of open on the side so that you can simulate the conditions for the exam. You know exactly, okay, I need a conversion here, or I need an equation here. Don't Google it. See if you can find it on the equation sheet. And then if you get stuck, then you can look in your textbook, or you can, try to Google the correct answer or whatever. But start with the material that you know you're gonna have, because come test time, that's all you're gonna have. So get familiar with your tools. But notice that sheet had no metric conversions on it whatsoever. You need to know the metric system in that box that we prescribed on that first week of class. All right, we still got about half an hour. What other items, questions would we like to talk about?
I have a quiz here that we put on that.
Okay.
And question 3 asks, which is a greater ionization energy in our heat.
Yes.
And I got it right, it was if, I couldn't explain why it was in.
Okay, so if we're comparing nitrogen and phosphorus, they're both in the same group. So it comes down to, we're talking again about ionization energy. Remember, there's a direct correlation, an inverse correlation between the size of the atom and how much energy it takes to remove electrons from it. So since phosphorus is a bigger atom, its electrons are more accessible. It's easier to remove them. So that's really the only argument that you need to make, is that phosphorus is bigger, and because it's bigger, its electrons are more accessible. It's easier to remove them.
I don't understand why they. It's the last problem is draw the 6p orbital.
Mm-hmm.
So I drew like all 3 dumbbells.
Okay.
Is that it's one number?
So the question itself was asking for a 6p orbital. So any of the dumbbells would have qualified as a correct answer for that. I wasn't asking for a specific like px, py, pz. I was just asking for, what does one look like? And so if it was clear that that's what that was, I gave you credit for it. Now, what I saw, and maybe yours was the one I'm thinking of, where it was unlabeled, it just was 6 lobes together without really any kind of labeling that they were actually different from each other. The reason I would have marked that incorrect is because that's very close to what an F orbital looks like. And I wanted to make sure there wasn't any confusion. And so that would be the reason why that would have been marked wrong, unless those orbitals were labeled separately as, okay, that's a P, this is another P, this is a third P. So I can see, okay, oh, he drew 3 P orbitals as opposed to an F orbital, which would look similar, but not quite the same.
Are all the quizzes different? Do they have slightly different questions?
Yeah, there are 10 different forms of each quiz. Now, the question types are all the same, but for security reasons and for other reasons that we don't need to get into, we have multiple forms so that it's harder for you to cheat off of each other. Especially since they're being given at different times in different locations. We don't want the people who are doing it Tuesday afternoon, for example, to have an advantage over those who are doing it Tuesday morning, or who have to take it on their own Monday afternoon because they don't have a lab session of their own.
Yeah, it was just asking that.
No, but you know, with limited exceptions. So like question 4, I think it was the essay question. All of you had different, or at least different variations on that one. And that was kind of the open-ended concept of quantum mechanics that we were going after in terms of, you know, some of them were easier than others. Some of them were, you know, getting into like, you know, why does one sublevel fill before another? Others were getting into concepts of quantization, explaining, you know, light spectra, explaining Bohr model of the atom. So there were lots of different ways that one could go. Which one you got was kind of just luck of the draw. But those were all things. I mean, that was in the chapter 3 review guide that you needed to know that information. So I thought all of them were fair questions, even if they weren't all of exact equal difficulty.
In the second review, review 2,
Okay.
I have one about abundance where it's asking for the abundance, percent of abundance, and it's giving you
Okay. This is another common homework question, but it is not a common quiz question or homework or exam question. What you're being asked to do there is you have to piece together kind of what's missing from the puzzle, if you will. So if I were to look at the average mass of antimony, which I can get off the periodic table, it is 121.76. We know that that average is the composite of the isotope antimony 121 times its abundance plus antimony 123 times its abundance. Now you look at that and say, okay, algebra, I can't solve 2 unknowns in the same equation. Well, that's where your mind has to kick in. If these are the only 2 isotopes, then there is a second equation that we can draw. And the second equation that we can draw is that 100% or 1 is equal to the total of whatever the abundance X is plus the abundance Y. Now we have a classic algebra 2 problem. 2 equations and 2 unknowns. How do you solve a 2 equation, 2 unknown? You set one of the equations to isolate a variable, and then you reinsert it into the first. 1 minus x is equal to y. And so I change this to 1 minus x. And now I have a simple algebra equation solving for X. X is the abundance of antimony 121. And then I can logically deduce what the abundance of 123 would be based on what 121 is. So again, for the exam, this kind of problem takes 15 minutes to calculate. You're not going to see that kind of problem on Friday. It would be pretty much the entire calculation section. Is it possible you see one of the other kinds of atomic mass where you multiply across and add? Absolutely. Those ones we can probably do in our sleep. They're relatively easy. But this kind, where we've got to break it down into algebra 2 concepts, yeah, it's a good challenge problem. It's not a very practical exam question. All right, we got about 15 minutes of my time left. Time for a couple more questions or examples, however you want to spend it. Go ahead. 23. Okay, here's an empirical formula problem. Now, remember our process for empirical formulas. We're going to take the percentages and turn them into grams. 47.08 grams of carbon, 6.59 grams of hydrogen, 46.33 grams chlorine. That was step one, turn all the percents into masses. Second step, turn all the masses into moles. So carbon, 12.01 grams per mole. So if I do that calculation, 47.08 divided by 12.01, 3.920 moles of carbon. Hydrogen, 1.01 grams per mole. 6.59 divided by 1.01 gives us 6.52 moles of hydrogen.
Okay, quick question.
Yeah.
So our periodic table says 1.008. It's not gonna change that much if we use that one, because that one gave me 6.538.
No, it's not going to change things that much. Empirical formula, we do a lot of rounding in anyway, because, you know, if we get 2.01 or 2.005 or whatever, we're going to round that to a whole number because the ratios are going to be whole numbers anyway. I'm going off of my rule of thumb. My rule of thumb is that for atomic masses or molecular masses, 2 decimal places is usually sufficient. We usually don't need to go beyond that, just because the differences start to be really, really small beyond that 2nd decimal place, especially in terms of what we can measure. Chlorine, 35.45 grams in every mole. So 46.33 divided by 35.45, 1.307 moles of chlorine. We've converted everything into moles. Now we need to start to reduce the fractions. To do that, we need to divide by the smallest number. So divide everything by 1.307. If we do that, that means we're gonna have 1 chlorine. Six 6.52 divided by 1.307. It's gonna give us 4.99 hydrogen. We're gonna round that up to 5. 3.92 divided by 1.307. We're gonna get 3 carbon. So since all of our numbers here are whole numbers already, we don't need to do any further modification. We just turn this ratio into a chemical formula. C3H5Cl.
Different order that you go in, sometimes offhand it will say like carbon, hydrogen, chlorine.
So I usually just do them in the order that I'm given. There's usually a reason behind it. Most of the compounds that we're working with here are going to be organic compounds. So I know it really doesn't matter if you put them in a different order. I'm not going to take that away from you because again, that's really not the point. The point is the process and going through and doing the process correctly. Understand that if we were doing this in an experimental kind of situation, there might be some naming conventions that we have to be aware of. So for example, organic compounds like these generally are carbon-based, so carbon's the first element that's listed, followed by hydrogen, followed by whatever else. But that's more on the experimental real-world application side. Right now, we're just focusing on the quantification, the process side. We can marry the two later.
Now, who changed that to a molecular one? Like, all that information.
So this problem doesn't ask specifically for a molecular formula. If it were, we would have to be given a molar mass of that molecular formula. And then whatever we would do is we would need to find the value of N. N is equal to whatever the molar mass is, divided by the empirical mass, which we can calculate 3 times 12.01 plus 5 times 1.01 plus 35.45. The empirical weight would be 76.53. So we could divide that number by 76.53. And whatever that number comes out to be, that's what we would multiply to get our molecular formula. And remember, N is always a whole number. So it's either going to be 1, 2, 3, 4, something along those lines. If it is fractional in any kind of way, that's either a telltale sign that we made a mistake or that we calculated the empirical mass incorrectly. Again, if it's close, if it ends up coming out 1.89, 2.02, we just round to the nearest whole number. Comes out at 1.5, 1.4, we know we did something wrong. But if it's close, then we could just round it to the nearest whole number.
You said close, like 1.1, was that close enough or? Okay.
Yeah. What we're trying to stay away from is the middle range between numbers. You know, if it's 0.1, give or take a little bit on either side, yeah, we can round that accordingly. You get into that 1.3, 2.4 kind of range, you're not close enough for rounding. You made a mistake somewhere.
Do we have any like those quantum number sets? Like if you give us this, we gotta figure out the M, the L, what valid, not valid.
Yeah, I personally love those kinds of questions. So yes, I would expect to see something along those lines. And that's probably more on the multiple choice side than on the short answer side. Just to give you some options for, you know, that's a good multiple choice question. Similar to what we had in top. Yeah, similar to one of the top hat questions where, you know, I gave you a series of sets of quantum numbers and you had to tell me which ones were good and which ones weren't. That's a really good way just for me to understand if you understand the limitations on the quantum numbers. And again, you know, just kind of going back to that discussion that we had at the time, understanding that the quantum numbers are actually related to the orbitals themselves. And they're not just a random pick of numbers, but that they actually have meaning. We can tell from the first two quantum numbers what subshell we're dealing with. You know, is it S, is it D, is it P, is it F? We can tell from those two numbers what energy level we're in. And then for the last two numbers, you know, getting it down to a specific orbital, one of two electrons, and then down to a single electron. Is it spin up or is it spin down?
That was the one I wanted to know. How would we know if it's the plus or the minus that one? That's the one I think.
The only way that you would know is if you were given orbital notation, the electron configuration with the arrows and the boxes. The arrows that are pointing up are spin up, +1/2. The ones that are pointing down are spin down, -1/2.
So we don't have that.
If you don't have that, you can't know. That's actually part of where the convention comes from. The actual up and down designation has to do with how the electron actually interacts with a magnetic field. Well, half of the electrons will actually orient themselves in one direction, the other half will orient themselves in the other direction. That's how we actually knew that there were two electrons in a given space, because of the way that the electron beam would bend when we put it in that magnetic electrical field. All right, we got time for maybe one more thought, one more question, if you have it.
My next question, it asked for question 5 asked for, it would give you a 5 week, they wanted to end out for it. And so I put 6, because I thought, for some reason I was thinking, because it's a D, like on the periodic table, that's normally n -1. But the answer is 5.
Yeah, so if we're given an orbital designation, that's telling us the energy level and the sublevel based on what we're told. So if we're told something's 5s, 5th energy level, s orbital. If we're told something's 5f, 5th energy level, f sublevel. Where that N-1, N-2 business comes in is when we try to identify what electrons, what elements would put electrons in there. So for that 5D that you're talking about, you're right. Elements in the 6th row of the periodic table would start to utilize that.
Okay, so that one 5. So 5 would be the end, but D would be 3, right?
D would be 2. S is 0, P is 1, D is 2, F is 3. All right, I think that's about it for now. Thanks for coming. Appreciate your efforts in coming here and trying to prepare yourselves. Hopefully this helped. If things come up and we have more questions between now and Friday morning, feel free to shoot me an email or remind, come to my office hour tomorrow at 1. I'll be happy to help you in any of those places. Have a good night.
Thank you very much.